Welcome to Math 1314. This is section 4.2. This is on exponential functions. Well, first off, what is an exponential function and what does it look like? Well, it looks like f of x equals b raised to the x. X is the variable part, and b, this base, is a fixed number. Now, it's not just any number. It can't be 0, it can't be 1, and it also can't be negative. So if it can't be all of those things, what are our possible choices for b? Well, b can be a number bigger than 1, or it can be a number that's a fraction between 0 and 1. That's our only choices. So for example, if there is a b bigger than 1, I could have b equals 2. So here b is 2, and we have 2 to the x. Here b is 10, and I have 10 to the x. Those are b's bigger than 1. I could have a b that's between 0 and 1. So in this case, b is 1/2. So that is 1/2 to the x. And I could have b is 2/3. And that would give me 2/3 to the x. So all of these are examples of these exponential functions. Now, one source of confusion is if you see -3 to the x. This is not -3 raised to the x, because remember, b cannot be negative. So what is this thing when you see it? Well, what it is -1 multiplied by 3 to the x. And the reason you know that is from what's called order of operations, which one comes first. And exponents take a higher priority over multiplication. Now, these things have a particular shape. And so if you have f of x is b to the x, and your b is bigger than 1, any b bigger than 1, it basically has this kind of a shape. Always crosses at 0, 1. It grows quickly on the right hand side, and on the left it shrinks down toward the x-axis, which is y equals 0, but it never gets there. It just keeps shrinking and leveling off, but never touches. The domain is all real numbers, and the range, since it never touches 0, has a parenthesis 0 up forever. If the particular b is a fraction between 0 and 1, it looks similar, but it's flipped around. It grows on the left and it shrinks on the right. Again, both of them cross at 0, 1, irregardless of b bigger than 1 or between 0 and 1. Both cases have exactly the same domain, and both cases have exactly the same range. Alright, so let's take a look here at 4.2 part 1 in the homework. We have g of x is 4 to the x. Alright, so the first question is b. What's b? Well, b is 4. That's bigger than 1. So it's going to have this basic shape. Crosses at 1 on the y-axis, levels off as it comes here to the left to y equals 0, which is the x-axis, and it grows to the right. If you want some values, if you plugged in 1, well, 4 to the 1 is 4. If you plugged in 2, 4 squared is 16. If you plugged in 3, 4 cubed is 64. So you can see it's growing extremely rapidly as you go off to the right. Domain is all real numbers. Range is 0 to infinity, but 0 is not included. Horizontal asymptote, the place it's leveling off to, is y equals 0. Alright, and just a rough sketch, 1, 4, 2, 16. So it does again grow quickly, levels off as we go off to the left. Domain and range we already talked about. Alright, question 2. We have 1/6 to the x. So b is a sixth. That means the particular b is a number between 0 and 1. So it's flipped around. Still crosses at 0, 1, levels off to the x-axis, which is y equals 0. Domain is all real numbers. Range is the same because this is not shifted anywhere, so 0 on up. Horizontal asymptote again is y equals 0. Alright, what about question 3 here? We have m of x is 5/4 to the x. So here we have that. So the question is b. Well, b is 5/4. So if b is 5/4, so b is 5/4, question is how big is that? Is that number bigger than 1? Or is that number a fraction between 0 and 1? Well, 5/4 is 1.25. That's bigger than 1. So it's going to have that particular shape for when b is bigger than 1. Crosses 0, 1. Domain is everything. Range is 0 on up. And the horizontal asymptote again is y equals 0 because it's leveling off here on the left hand side toward y equals 0. Alright, in question 4 we begin to look at what happens when we shift something. Alright, so first off, we have 5 to the x. Basic shape for 5 to the x is this shape. But we have a +3 on the end, which moves the entire graph up by 3. Now, the entire graph. So let's see. Normally it's at 0, 1. So if you go up by 3, 1 plus 3, it's now crossing at 4. All of this goes up by 3. Even the place that it's leveling off to. So it used to be leveling off to y equals 0. That gets bumped up too. And so the new horizontal asymptote is y is equal to 3. The domain does not change. The range does because it never gets any lower than 3. Not even touches 3. And so we get 3 to infinity. Horizontal asymptote is y is equal to 3. Alright, in question 5 here, let's see. We have n of x is 4 to the x minus 2. Now notice there's a difference here between 4 to the x minus 2 and here 4 to the x minus 2. Where is this minus 2? The minus 2 here is on the end, and that means I've gone down by 2. When it's up here with the x, then it's a left or right. X minus 2 is 0, so we go to the right. So basically, we're going to take our shape and now shift this to the right by 2. Alright, so here was where it used to be at 0, 1. If that shifts over by 2, that's now located at the point 2, 1, whereas before it was located at 0, 1. So it got moved as well. The rest of the graph gets shifted as well to the right by 2. Domain doesn't change. Range doesn't change. Why? Well, we didn't move anywhere up or down. Horizontal asymptote stays the same because we just moved left or right, and in this case, right. All right, question 6 here. We have 2 to the x plus 4 plus 1. All right, so a couple of things. B, what's B? Well, B here is 2, and so we know its basic shape is going to look like 2 to the x. And if we graph 2 to the x, it looks like the following. Crossing at 0, 1. So this is anytime b is bigger than 1. So in our case, what's going on? We have this plus 1 on the end, which means it's going to go up by 1. I've got the x plus 4, so that's a left or right. I get x is minus 4, so we go to the left. All right, so let's see our graph. Used to be at 0, 1. I'm going left and then up. So let's see. We're at 0, 1. We go left by 4. So that's minus 4 up by 1. Okay, so it used to be at 1. Now this point has gone over. This point has gone over and up to now minus 4, 2. Everything's moved up, so here's the old horizontal asymptote. We go up by 1, and so that's now at y is equal to 1. Question 7. Question 7 has that thing we talked about earlier, minus 2 to the x. What comes first here? Well, not the minus. Minus 2 to the x is not minus 2 raised to the x. What it is minus 1 times 2 to the x, and so it's just a flip about the x-axis. So normally 2 to the x is here. We have our horizontal asymptote, y equals 0. Take this whole thing and flip it about the x-axis. It flips down. It's now crossing at 0, minus 1, but everything else stays the same. Domain does not change. So that's still minus infinity to infinity. The range does, though. Since it's flipped over, the highest it ever gets but never touches is 0, and it goes down forever. So minus infinity to 0. In question 8, we get to see a new number, and this new special number is a lowercase e. E is a famous number just like pi. We know pi does not repeat, it goes on forever. It's about 3.14. And E is another one of these special numbers, and it is about 2.7182. So it's a legitimate B for us to pick. And that's the particular B we have here. So I look at this, I see it's up with the X, so it's a shift left or right. So I get X minus 2 is 0, I get X is 2, and so the graph has got shifted to the right by 2. So when you see the thing in blue here for normal e to the x, it looks just like every other b to the x where b is bigger than 1. And so we just get shifted over. This was at 0, 1 normally. It's now moved over by 2, and this is at 2, 1. Domain and range are the same for all exponential functions. Horizontal asymptote is still the x-axis, which is y is equal to 0. Okay, now the second part of section 4.2, we talk about banking. We'd like to invest some money. P, capital P, is called the principal. It's the amount of money we have right now. Capital A is the amount of money we're going to have at a future time. And T is usually used for time. So this amount of money we have in the future is the principal that we have now plus any interest that we've earned. T is time, and it's usually in years. Now, if for some reason the problem gave it to you in months, you need to convert it to years, and so you would then just divide the number of months by 12. So let's say it was 24 months to make it easy. Then it would be 24 divided by 12, which is 2, which is 2 years. So again, if the time were in months, you would just divide it by 12 to get the number of years. R is the annual interest rate, and that's usually written as a decimal. So if they said 3% as the annual rate, then divide that by 100, and that gives you R is 0.03. If it is 5.1%, then R is 0.051. N is what's called the number of compounding periods, this small letter N. And it's how often the interest is calculated and then re-added back into the principal. So it's an ongoing process. If this is done once a year, this is called annually, or N is 1. Biannually, N is 2. It's twice a year. Quarterly means it's done 4 times a year. Monthly, N is 12. Weekly, N is 52. And daily, N is 365. So again, we've got some money now. P is the principal. We're going to put it into the bank. The bank is going to give us an interest rate. It's going to sit there for a particular time. And we have a certain number of compounding periods. And then we're going to get our money back out at a later date. Now we have some formulas that will calculate some things for us. So if we have a certain number of compounding periods, so here we are at the number of compounding periods, we have the formula is the amount A is the principal times 1 plus my rate divided by the number of compounding periods, and then we have N again multiplied by the length of time. So the number of compounding periods appears in two places. If the interest is calculated continuously all the time, then the number of compounding periods runs off to infinity, and we get a new formula. And this is the formula for continuous compounding. Well, let's see. It's still the principal, but now it's multiplied by our friend E raised to our rate times the time. Some tips for our calculator. You can use this key that has a plus/minus, or a key that looks like a parenthesis with a minus in the middle, and that'll change the sign of something from plus to minus. If we need an exponent, exponents look like either y to the x or this upward pointing caret for exponents. If we need the e to the x function, sometimes it's on a key. For example, on your iPhone, it is on a key. If it's on a calculator, it's often sitting above a key. So you're going to have to use a shift or a second to access it. All right, in question 4 here, the beginning of part 2, we are given $15,000 right now. The money's going to sit in the bank for 14 years. The rate is 3.7%. So as a decimal, I divide by 100, and I get that R is 0.037. So here's our formula, and that's for a fixed number of compounding periods. So again, we notice, scroll up a little bit here. So we notice that annually N is 1, quarterly N is 4, monthly 12, daily 365, and continuously there is no N because N ran off to infinity. And they want you to take each of these N's and calculate the amount of money you would have after that time period. So I've done this for N equals 12. So here's the principal is 15,000. N is 12. Length of time is 14. My interest rate is 0.037. N again is under here as the 12. So from this step to the next, what did I do? I just simply multiplied together the 12 and the 14 to give me the 168. So now this looks quite complicated. Where do you start? You start here on the inside. Don't try to start on the outside. The easiest is to start here on the inside. Now the next important tip is don't try to write anything down. If you write anything down, it's going to be rounded too much and the answer probably will be wrong. So start here. You would do 0.037 divided by 12 equals or enter so it does the calculation. Then you do plus 1 equals again so it does that. Then you need the key to do exponents, which we saw was y to the x, or the upward caret. You enter 168. Now, it may or may not need an equal to calculate it. And then finally you multiply that by the 15,000 and hit equals or enter. So again, to do this ugly calculation, start here on the inside. Do this division, plus 1 equals y to the x, 168, multiply by 15,000, and then press equals. Now, they said round it to the nearest cent. Alright, so I'm looking at the nearest cent. The number after this 4 is a 5. If it's 5 or bigger, you round the number up, and so the 4 becomes a 95. And so you would do this for n equals 1, 4, and also 365. What about continuously? All right, so for continuously, we have p multiplied by e to the rt. All right, so fill in p, fill in r, fill in your time. So the first step in this is to do this calculation, and I get 0.518. You then need to calculate e raised to that item. That's where you're going to need to use your e key. So once you get e raised to that number, multiply it by 15,000, and you get 25,180.004. And if I round this to the nearest cent, well, the 4 drops off and I get 0.00. Now, that's the best you could ever hope for, is continuous compounding. Notice this number is better than monthly, not by a lot, but it is some dollars more than monthly. All right, let's see. In question 2, we're just doing continuous compounding, and they're going to have you change the interest rate, fix the time at 11 years, principal is 16,000. So I did this for 4%. So 0.04 multiplied by 11 is 0.44. E raised to that number, get that, multiply by 16,000 equals. All right, I get this big number, and I'm going to round it again to the nearest cent. So let's see, I'm looking at the 5 here after this 1, so nearest cent. The number after the 1 is a 5, so increase that to be a 2. So you would do it again for the other 2 interest rates. In question 3, we just have a simple calculation. We're looking at radioactive decay. There's a lot of extra words in all of that. The key here is the formula, the amount of a substance that we have after a time equals 20. This 20 is how much we started with. It's the initial amount of the substance in the radioactive decay. That's where this 20 came from. Over time, the product decays. So what's going on here is the following. we're starting off with 20 micrograms of this strontium 90, and as time goes on, it keeps decaying. We're losing half of it after particular time periods. That's this thing called a half-life. So it basically halves every 28.9 years. So after 28.9 years, after 28.9 years, we are down to 10 micrograms. And so every 28.9 more years, the substance will halve. So the question here is, after 144 and a half years, how much of this substance is left? Well, we simply plug in for the time, 144 divided by 5. When you make this calculation, it's a nice number, and so it turned out to be 5. A half is 0.5. So now I simply need 0.5 raised to the 5, get that number, and multiply by 20. So we have 0.625 micrograms of this substance left, and I rounded it to 3 decimal places. All right, and finally, in question 4, we have something called Newton's law of cooling. Sounds complicated. It's an ugly looking formula here. But what's going on is something that we all understand. Take something hot out of the oven, put it on the counter in room temperature, and eventually it's going to cool off so we can eat it. So this formula actually tells me the temperature of the object at a particular time. Now, let's see. What is this? What is this TA business? The TA business is the temperature of the room. So, if you put it in a freezer, it would cool off faster. If you leave it sitting on the counter, well, that's the temperature in the kitchen. What about this T0? T0 is the initial temperature when it comes out of the oven. Comes out of the oven, it's hot. All right, E. E is our function which dictates how quickly this thing is cooling off. The minus means that we're cooling down, right? So this particular item, we are coming out of the oven, in this case, at 400 degrees. It starts cooling off. Well, it can't cool off any more than our room temperature, which is 77. All right, so comes out of the oven at 400, cools off, but it can't get any cooler than the room temperature of the kitchen. How fast it cools is this K, and they give us the value of K is 0.046. Alright, so while complicated, it's a common thing. Take hot cookies out of the oven. They have to cool off. When they cool off cool enough, we can eat it. Alright, so let's take a look here. If I plug everything in to our problem, we had room temperature, which was 77, comes out of the oven at 400. That difference is 323. Here's my K that dictates my cooling. So, what's the temperature after it sits there for 20 minutes? So here's my time of 20. Plug it in. Do the multiplication, so I get e to the negative 0.492. So now I need to make that particular calculation. And when I make that particular calculation, I multiply it by 323. And once I do that, I add it to 77 to find out that after 20 minutes, it's cooled down to 205 degrees Fahrenheit. So it's come down from 400. All right, so in our last case, let's see. We would like to figure out if after 50 minutes it has cooled down to 100 degrees or not. Because according to the recipe, it has to be there before we can put the icing or frosting on the top. So again, let me make our graph. We start off, comes out of the oven at 400. We know it never can get any cooler than room temperature, which is 77. So we know that this thing is cooling off over time. 20 minutes, and we saw we were down to, at this part, about 205 degrees. Question is, after 50 minutes, are we cooler than 100 or not? So let's see, plug in the 50, do the calculations, and I get 109.383. They say round it to the nearest degree, so that's 109. So it is too hot. You can't put the frosting on the cake. Well, you could, but the frosting would melt off the sides and run all over the place. So no, you have to wait a little bit longer before it's going to be under 100 degrees. I wonder how long that would be. Can you find it?